I'm Rob Inkster, CEO of Tactex Controls. We've built some very cool touch sensing products in the last 5 years that are currently being used in the music and graphic arts markets. Today I'd like to tell you a little about our technology and show you a product concept that will make people think different about the keyboard. At Tactex, we develop and manufacture sensors based on technology that we developed for the Space Agency as a touch sensing skin for robots. With woven fiber optics, we can manufacture very thin materials like this that act like human skin. They can sense where they're being touched and by how many fingers and with how much pressure. The materials, called Kinotex, contain a dense array of individual sensors called taxels, which simultaneously sense pressure everywhere on the material's surface. When the electronics are connected, a pressure image of the surface is produced. Here's an example of a Kinotex-based product. The MTC Express is a multi-touch pressure-sensitive touchpad controller used in the music industry. We process the image that you see here and use it as a two-handed control for computing applications. Kinotex is ready for the mainstream computer input device market as a core keyboard technology. What I'm going to show you is the flip keyboard, a concept disclosed by Bill Buxton when he was at Xerox PARC. Finally, we have a technology that enables this concept to be manufactured at a low cost. Here's how it works. This keyboard uses Kinotex as the sensing technology to determine which keys are struck and when. The Kinotex is installed underneath the keys. The keyboard looks and feels and acts exactly like a traditional keyboard. It even costs the same to manufacture. The innovation is on the flip side. This touch control surface is the same piece of Kinotex being touched from the other side. Flipping the keyboard over disables the regular keyboard and activates this large sensing surface. The keyboard now acts as a two-handed, configurable, pressure-sensitive touch controller. Here's some immediate applications in music, video mixing, and education. First, let's configure the surface as a musical instrument. A simple overlay template here gives a sense of visual feedback. In this case, we're enabling two different musical instruments. The right hand can control a 9-note polyphonic synthesizer like this. While the left hand can control a looping backbeat like this. Okay, now here's another musical example where we want a mixer to control the sound. Here's a different template which provides both tactile and visual feedback. With this particular application, it's possible to train the surface first by indicating a control on the GUI with the mouse and then showing which fader you want to run that control. Then, in run mode, the faders work just like you'd expect faders in a real mixer to perform. Next, we have a video application. Video editing can use its own set of custom controls. Here we have a set of transport controls and programmable buttons that are used with applications like iMovie or Final Cut Pro. Note that we're not replacing the mouse. The right hand operates the mouse as a selector, and the non-dominant left hand works with navigation and command tools. You can easily imagine how this kind of two-handed functionality makes the job faster and more intuitive in CAD and animation apps. So far, I've been talking about creative users and power users. What about the kids? We think the flip keyboard has a huge application in education. Suddenly, the computer is something you can grab a hold of and manipulate and configure. The pre-K to grade 2 age group is exploring hand-eye coordination, spatial relationships, learning language skills, and having fun doing it. The kids' traditional input devices are finger paints and dolls, blocks and drawing tools, all of them with rich tactile interfaces. The flip keyboard can be configured to emulate these kinds of interactions. For example, a simple mapping of the alphabet like this makes an engaging interface for youngsters that would be intimidated by the QWERTY keyboard. In the grade 3 to 8 age group, of course, the kids are much more familiar with the mouse and keyboard environment. Now the learning experience turns to arithmetic and science. Students can make their own templates using the classroom color printer. They can build their own touch interfaces that emulate pinball games, rocket ship controls, an Etch-a-Sketch, or a drawing tablet. We can just imagine what will happen with the flip keyboard in education. Creative youngsters will teach the rest of us how to think different about this new mode of touch interaction with the computer. We're looking at a product concept here that involves radical evolution. The keyboard which is the most familiar of all input devices and which owns a huge piece of real estate on all of our desks, is completely unchanged. It doesn't change in terms of form and function and feel. It even costs the same to manufacture. But a radical new dimension is introduced when you flip the thing over. Suddenly, two-handed, expressive, intuitive controls are enabled. This kind of functionality is immediately valuable in education and music and video processing apps like we've just shown, and opens up a whole new range of applications, a whole new range of interactions with the computer. Further into the future, with parallel advances in operating systems, we're going to see a whole new way of interacting in 3D with the computer as a result. And 5 years from now, we'll probably look back and wonder why we spent so long working with the old QWERTY keyboard.